Okay, this is more about angles and circles. Let's remind ourselves that as we bring in an angle into the circle, first it intercepts a small arc when we get to the middle. That's the definition of the measure of the arc is the same as the measure of the central angle. It gets bigger as we go across. Okay, what if we do this with an X? It's still going to work with an X, so ignore this part of it and see that it's just the same thing. But then, as we come in, say we're talking about this right angle. As it comes into our circle, again it gets bigger as we get to it. It gets to the middle. Now the angle at the right is a central angle. Its measure is the same as the measure of the arc. That's how the arc measure is defined. Oh, but it's got a vertical. This is the same angle over here, and the measure of the arc is also from the central angle. That's the same. So this arc is the same as this arc in measure. So if this is a 50-degree angle, so is this one. This is a 50-degree arc. This is a 50-degree arc. So notice all of the arc intercepted by these two intersecting lines is 50 here, a total of 100 degrees, the measure of the two arcs. Well, one way, which is kind of long and you wouldn't do it just for this, but it would still work, would be to say that a way to find out the central angle is to take the average of 100, of 50 and 50, 100, or 50. Well, that just gets you back where you started, but it's kind of helpful for what we're about to do. So if you take intersecting lines, you take the two arcs that they intercept, average them, that will be the central angle, or the measure of the angle that's in the center. In this case, it is a central angle. But if we move it away from the center, does it still work? Well, I didn't change the angle. The angle's staying the same. I wrote it here with black ink. I mean, it's not changing. It's still a 50-degree angle, and its vertical is still a 50-degree angle. But look what's happening to the arcs. When I start over here, little arc, big arc. Comes over here, big arc, little arc. But if we're going to sit and play with it and figure out with it, we're going to see eventually that it stays the same. The two still add to 100 degrees. Well, why is that? Well, conceptually, let's think about why it is. The circle is round. It is round. That means it's the same curvature on both sides. It's round. So what? As I move my X to the right, the left arc that's intercepted gets larger and the right one gets smaller. At the same rate, this gets bigger, by the same that gets smaller. The circle giveth, the circle taketh away. And it stays a constant 100 degrees to add the two together. The measure of the two arcs together still stays 100 degrees. Why? Because over here the circle giveth, and here the circle taketh away. Why is it the same? Wouldn't be for other shapes, but it's the same for a circle because the circle is round. Since it's round, it's the same over here that it is over here. So as this giveth from the circle, this taketh. The circle taketh from it. Okay? It remains a constant, in this case, 100 total arc measure. Okay? So again, what can we do? Measure this arc, measure this arc. If we know the measure, we know the measure. Add it up, divide by 2. That'll give us the measure of the angle. And it's vertical. Hopefully you can see that happens. It's when it's all crookedy, it still works. Because notice, no matter which direction I go, if I'm looking at these two vertical angles, when I move, one gets it taken away, the other gets it given to it. And it's in the same rate no matter where I do it. Why is it the same rate no matter where I do it? Because the circle is round. So it's not going to matter where you do it. It's going to take away and it's going to give the same. The circle giveth and the circle taketh away. And for that, we have a theorem about angles inside of a circle. If two chords intersect inside a circle, then each angle is the average of the measures of the arcs intercepted by it and by its vertical. So we here have the red angle 1, it's the average, add them up and divide by 2, add and divide by 2 of the 2 red ones that are intercepted by it in this article. The green is add up the 2 arcs that are intercepted by it in this vertical and divide by 2. Let's look at our circle again and come up with some more things to do here. Just saw was that if you take and any place here in, put an X in the circle, no matter where you do it, when you move it around, it's still going to be add the 2 arcs and divide by 2. If it's on the edge, oh, well, yeah, that kind of works because I'm adding nothing intercepted here and all of it added here and dividing by 2. Well, that's just the same as the intercepted arc. It's a more general statement. So nothing added up, there's nothing on that side because that side doesn't, that vertical doesn't intercept anything, and all of it divided by 2, that's the same as the intercepted arc theorem that we just talked about. So any place that you go with an intercepted arc or inside of your circle, it'll get bigger, it'll give it away, giveth and it taketh away, no matter where you are, giveth it all away and taketh it. Add them up, divide by 2. You're adding nothing to something, and dividing by 2 is the same as just dividing the something by 2. Okay, what happens then when we have this situation? Okay, the intersection is on the circle, but the angle is not inscribed. I wonder what happens when that happens. Okay, let's look at it here. Say I've got to do it with a 45-degree angle, which I'll estimate here. Okay, well, let's look at how angles work here. Got an angle that may be 45, but I'm going to do it around like this. How big could the angle be as I rotate it? Well, it could be all the way down to nothing, and it could be all the way up to 180. So the possibilities are 180 degrees in a line. If I'm going to take it at 45, what portion of the line's total possible degrees would that be? Well, I think you can see that 45 out of 180 is 1/4. There's a half. If I do it up to here, it's half. Over to here, it's 135 degrees out of 180, which is 3/4. So let's start with 45. And look how that compares to the circle. Because remember now we're relating it to the circle, and we want to know how you can find the angle when you know the arc, or vice versa. Well, I know that this angle is 1/4 of the possibilities that the angle could be. It's 45 out of 180. Well, what is it relative to the circle of the whole 360? Oh my goodness, it's 1/4. What a coinky-dink. It's not just a coincidence, it's actually proportional. So when I have my line at 45, it's 1/4 of what the line is. When I put it with the circle, it intercepts 1/4 of the circle, as you can see here by the central angle. It also works when you come up. I can do it with other ones, but these are easy to do. When you come up to half, that's half of the lines, it's 90 degrees, half lines 180 degrees, and the intercepted arc now is 180 degrees, it's a semicircle, or half of the whole circle. When I go to 135 degrees, it's the same deal. So now we have 3/4 of the available 180 degrees for the line, and again 3/4 of the circle is here. As you can see when I put in the central angle, 3/4 of the circle, 3/4 of the line. So So what do we have? I'm going to write out a bit to try and explain what's going here a little bit, help you get an idea. So if I have, I'll fix it back. We can see what's going on. Okay. What are we seeing here? If I write it out as a proportion, because it is proportionate, we've demonstrated it, we haven't proven it, but it is. So let's look how that works. One thing. There we go. So I'm going to do the parties to the whole, typical proportion strategy. So the part of the line would be the angle, the full 180 degrees. The part would be the whole would be the line. And for the circle, the part would be the arc, and the whole would be the circle. Okay. Well, how many degrees are there in a line? Well, there's 180. How many degrees are there in a circle? 360. So let's solve this. And so that'll be 360 times the angle is 180 times the arc. So we can solve for either the angle or the arc. So we get 2 times the angle is the arc. Or if we solve the other way, the angle is half of the arc. So the relationship of the measure, oh wait, that's the same relationship we just found inside the circle. The angle is half of the arc that's intercepted. The arc is twice the angle. So what do we have? It works all inside the angle, inside the circle with any inscribed angle, but it also works just as long as the intersection is on the circle. It will work. So as long as the intersection is on the circle, either as an inscribed angle or as what we have here, which is the intersection is on the circle, but the angle is not inscribed. So if we have an X inside, it works. If we have any place inside,
Katie Vecinos, if you're in the building, come to the office. Katie Vecinos, if you are in the building, come to the office.
We have anywhere here inside the circle, it'll work, and anywhere if the X is inside the circle anywhere, or the vertex inside the circle anywhere, or on the line anywhere, this relationship stands. It's 2 to 1. 2 angles is the arc. So we have that here in a theorem about a tangent or a chord and the relationship to the arc. Well, let's carry this one further. How will that be? I'm going to start with my circle and with my X, and I'm going to see what happens. Here's my circle and here's my X. So we did it with just an angle, and we saw that, of course, the definition of the arc measure is the angle at the center. It's smaller or it's bigger, but when you pull it back twice as far away from where it entered, that the arc will be twice as big as the angle. And we saw that any place in here, first off, if it's at the center, you can average the two and you still get the central angle. But as we pull, the circle giveth and the circle taketh away. And it is the same amount because the circle is round. The curvature makes it that way.